In section 4.2, we're going to talk about a couple of concepts that we're not familiar with the terminology, but we are familiar with the concepts behind these terms. First of these is the null space of a matrix. We say the null space of an m by n matrix A, written as null A, is the set of all solutions to the homogeneous equation Ax equals 0. Okay, so null A is simply a set of all x such that x is in Rn and Ax equals 0. Okay. X has to be in Rn because if A is an m by n matrix and we want to be able to multiply A times x, then there must be an entry in x for every column of A, and so x must be from Rn. So null A is simply the set of all solutions to Ax equals 0. The fact that we're calling it the null space probably gives you a clue that it's a subspace, and indeed it is. The theorem here says the null space of an m by n matrix is a subspace of Rn. Let's look at this matrix A given here. To generate an explicit description of null A, we have to solve Ax equals 0. Right? An explicit description means you can look at it and generate an entry in null A. Okay, so to do that, we have to solve Ax equals 0. So we throw that into an augmented matrix and do a couple of row operations, giving us the matrix given here. So we see the general solution is x1 equals 6x2 plus 2x4, and x3 equals negative x4, and x2 and x4 are free variables. If we put it in parametric vector form, we have x1 is 6x2 plus 2x4, x2 is just x2, and so forth. So notice that any vector in the null space of A is a linear combination of these two vectors given here. So if we put those, if we look at those, we can say any vector in the null space of A is in the span of those two vectors. If you remember the theorem from section 4.1, it said that if you can write your set as the span of a finite set of vectors, then it's automatically a subspace of that parent vector space. So here we've written, for this particular matrix A, we've written the set of solutions to Ax equals 0 as the span of these two vectors, so therefore the null space of A is a subspace of R4. The second concept that we're going to talk about here in this section is the column space of a matrix. And once again, it's new terminology, but not new fundamental material here. So the column space of an m by n matrix A, which we write as col A, is the set of all linear combinations of the columns of A. Right? All linear combinations of the columns of A. We know that to be the span of the columns of A. Right? So if A is equal to A1 through AN, the column space of A is just the span of A1 through AN. Since we've the definition here is that column space of A is the span of a set of vectors, so it too is a subspace of some vector space. In this case, if A is m by n, then the column space is going to be in Rm, because when you take a linear combination of vectors with m components, you're going to get another vector with m components. So the column space of A is in Rm. Another way to look at the column space of A is to write it as a set of all B, such that B is equal to A times X for some X in Rn. Because when you multiply A times X, you're simply taking a linear combination of the columns of A. Here's a set S defined in terms of this generic vector, and you're asked to find a matrix A such that S is equal to the column space of A. So we simply take that generic vector, write it in parametric vector form, So we can write anything in S as a linear combination of these three vectors given here. So if we put those vectors into a matrix, then we can say that anything in S is a linear combination of the columns of A, and so S is equal to the column space of A. As I said before, the null space of A and the column space of A are simply new terms for describing entities with which we are already familiar. Null A is just the set of all solutions to AX equals 0. Right? That dates back to like section 1.3, 1.4, somewhere back there. A column space of A is just the set of all linear combinations of the columns, or the span of the column. So again, we're going back to fundamental information that we learned in chapter 1. Okay, so if we have a matrix A, how do we determine if a particular vector X is in the null space of that matrix? Well, go back to the definition. Null space of A is a set of all vectors satisfying AX equals 0. So we just need to multiply A times X and see if we get 0. Again, to multiply A times X, we're taking a linear combination of the columns of A, so there needs to be a component of X that corresponds to each column of A. There are n columns in A, so we need n elements in the null space of A. So null A is in Rn. Okay, so here's a vector, and we're asked, is this in the null space of the given matrix? So we simply multiply the matrix times this vector, so that we're taking a linear combination of the columns here, and go through the arithmetic, and we end up with a 0 vector. So the answer is yes, it is in the null space of A, because A times X is equal to 0 here. Alright, what if we have a matrix A and another vector, and we want to know if that vector is in the column space of the matrix? So again, look at the definition. B is in the column space of A if AX equals B is consistent. So we need to solve a system to determine if B is in the column space of A. And again, the column space of A is going to be a subset of Rm, because we're taking linear combinations of vectors with m components, and so we get another vector with m components. Alright, so here's a vector, and we want to know if it's in the column space of A for the given matrix A. So we need to solve the system. Alright, set up the augmented matrix, solve the system. So I've done that, left out the specifics of the row operations, but we end up with this matrix here. And so the question is does this correspond to a consistent system? And the answer is yes, because we have no rows 0, 0, 0, something not 0. The fact that we have a row of all zeros is really irrelevant. The fact that we have free variable is irrelevant. The only thing that's relevant is that we don't have a row that's 0, 0, 0, not 0, because that would tell us it's inconsistent. So since the system is consistent, that means that this vector is indeed in the column space of A. Alright, let's look at this example. Here's a set W, and we're asked, is it a subspace of R4? So we can write any generic element of W as a linear combination of these two vectors. So we write it in parametric vector form. And so we can say that W is equal to column space of this matrix. Just taking these two vectors, sticking them in the columns of a matrix. The column space of this matrix is all linear combinations of these columns, which is exactly W. So that means that W is a subspace. Alright, how about this example? This one, it's not so easy or so clear to see, because we have this constant term 1 here, and so we can't write this set as a linear combination of vectors. So in this case, we have to go back to the definition of subspace. That's those three properties that every subspace must satisfy. So first one was, does it contain the zero vector? And if we look, for it to contain the zero vector, clearly D has to be 0, which would mean that the second component would be 2 times 0 plus 1, which is 1. And so if you get 0 here, you're going to have 1 up here, and therefore the zero vector is not in this set. So it is not a subspace of R4. About this set, is this set a subspace of R4? So we've got all vectors A, B, C, D that satisfy these two equations. There's actually two ways we could go about doing this using what we've learned in this section. One is easier than the other. Let's take the hard way first. We're going to try to write S as the column space of some matrix A. So we need to figure out what A would be. We're going to simplify things a little bit. Instead of C here, we're just going to substitute A plus 3B. And then instead of D, we're going to substitute A plus B plus C, but we're going to plug in what C is since we've gotten rid of C. So D is B plus C plus A, and C is A plus 3B, so we plug that in for C, and we end up with D equals 2A plus 4B. So we can write any vector in S in this form. So we replace C with A plus 3B and D with 2A plus 4B. And then it's just a matter of writing that in parametric vector form and throwing those columns into a matrix. And so S is equal to the column space of A, where A is given here, and thus S would be a subspace of R4, since the column space of any matrix is a subspace. Now the other way to look at it, so I rewrote the problem here, the other way to look at it is to note that we could write S in this form. So basically I've taken these two equations that we have here, and I've taken all the variables over to the left side, and so we've got zeros on the right. And so when you see zeros on the right, you should think, that's a homogeneous system. So we can write S as the null space of A, where A is equal to the coefficient matrix from this system of equations. So you see 1, 3, negative 1 for A, B, C, and then 0 for D, and from the first equation. And then the second equation, we get 1 times A plus 1 times B plus 1 times C minus 1 times D. So that's where this second row comes from. So remember what the null space of a matrix is. It's just the set of all solutions to AX equals 0. And so I've just taken this system of equations, written it, or taken these equations, written them as a homogeneous system, and then I can use the fact that the null space of a matrix is always a subspace, and we're done. So that's why I said one was harder than the other. This is clearly the easiest way. All right. Let's revisit the concept of linear transformations for just a bit. And this is again back to chapter 1, where we talked about linear transformations. One new term that we didn't learn back in chapter 1 was the idea of the kernel of a linear transformation. And the kernel of a linear transformation is simply the set of all vectors that map to the 0 vector. So the kernel of a linear transformation is exactly the null space of the matrix that defines the transformation. So kernel and null space are analogous concepts. The range of a transformation is a set of all vectors that get mapped to. So the range is in the codomain. Okay, sometimes it's all of the codomain, sometimes not, but it's the range is a set of all vectors that get mapped to by some vector from the domain. And so the range of T is actually the column space of A, where A is the transformation the matrix that defines the transformation. So the kernel of the transformation is the null space of A. The range of the transformation is the column space of A. Okay, last I want to talk about just looking at the contrast between the null space of a matrix and the column space. These really, on the surface, are very different sets. We will kind of pull them together a little bit later on in this chapter, but for right now, they're really very different sets, and they don't share. They share analogous sorts of ideas, but that's kind of the extent of it at this point. So let's assume A is an m by n matrix. Then the null space is in Rn, the column space is in Rm. The null space is implicitly defined. That means you're given a condition that vectors in the null space must satisfy, but you can't look at a matrix A and know which vectors are in it. You have to solve that system AX equals 0. On the other hand, the column space of A is explicitly defined, right? Because it's just the set of all linear combinations of the columns. So you can look at the matrix A and you know that the columns that you're looking at are actually in the column space, and you know how to create more entries in the column space. All right, to find vectors in the null space requires work. You have to solve the system AX equals 0. Note, however, that the 0 vector is always in the null space of A, right? Because A times the 0 vector gives you the 0 vector. To find vectors in the column space of A, you just compute linear combinations of the columns. So it's a direct process to do that. There's no obvious relationship between null A and the entries in A. On the other hand, the relationship between A and the column space of A is obvious since each column is in the column space. The typical vector V in the null space satisfies A times V equals 0. Typical vector in the column space has the property that AX equals V is consistent. Okay, so for null space, you're multiplying A times V to see if you get 0. To see if a vector's in the column space, you're solving a system AX equals V. So V is on the right-hand side in that case. Given a specific vector V, it's easy to determine if V is in the null space. You just see if A times V is equal to 0. To determine if V is in the column space, you have to solve a system of equations. All right, the null space equals only the 0 vector if and only if AX equals 0 has only the trivial solution. Okay, so how do you get what's in the null space? We have to solve AX equals 0. And if you get only the trivial solution, then that means there's only one solution, which is a 0 vector. The column space of A is equal to Rm if and only if AX equals B is consistent for every B in Rm. Right? That means that everything, no matter what you put on the right-hand side, the system will be consistent. So every B is a linear combination of the columns of A. And then relating it to linear transformations, the null space of A is equal to the 0 vector only if and only if the transformation x to AX is 1 to 1. So if you back up to the previous one, we had that null A is equal to only the 0 vector if AX equals 0 has only the trivial solution. And remember, that's going to occur when you have no free variables and or if there's a pivot position in every column, and so we know that indicates that the transformation is 1 to 1. And then the column space is equal to Rm if and only if Ax equals b is consistent for every b. So that means every b in the codomain gets mapped to. So the transformation must be onto Rm.